discussing about torque and second condition of equilibrium. Now let's start from the definition of torque. Torque is one effect of force which is rotational or turning effect of force. Torque is the rotational or the turning effect of force, and its unit is Newton meter, and this Newton meter different from Joule because torque is a vector quantity. Typically torque tau is equal to, it is the cross product of the position vector and force, both a displacement and force vector quantities. Hence torque is equal to R, magnitude of R, times magnitude of force times sine theta. And the direction of the torque is determined using right hand rule. If those displacement and force parallel, then torque is equal to 0, because the cross product of two vectors is 0 when they are parallel. And if both position vector and force given in a vector form, if force F equals Rx I plus Ry j plus Rz k, and displacement or position vector which is Rx I plus Ryj plus Rz k, then the cross product of position vector and force which is equal to torque, then torque tau equals R crossed force, which is I, j, and k. First, we write the component of a position vector which is Rx, Ry, and Rz. Then the component of the force which is Fx, Fy, and Fz. In this case, from matrix rule, the sign for I positive, j negative, and k which is positive. Then the cross product of these two vectors, torque equals first column, first row, then the determinant Fz Ry minus Fz Ry minus Fy Rz Fy Rz. What about the direction? The direction is I plus, again, the sign for j which is minus, into Fz Ry minus Fz Ry minus Fy Rz direction j, plus, when you solve the component of k, Fyrx minus Fyrx minus Fxry. The direction is in the direction of k. Therefore, torque tau equals Fz_Ry minus Fy_Rz in the direction of I, minus, when we distribute minus into the bracket, then minus times minus, it becomes plus, hence this becomes plus, and minus times minus plus, Fy_Rz, Fy_Rz, minus times plus minus, hence minus Fz_Ry j plus Fy_Rx minus Fx_Ry is the cross product of position vector and force vector, which is torque. Now let's see example. Example, if position vector are 3i plus 2j plus 4k and force I plus 3j plus 6k, then torque tau equals, first write I, j, k, a unit vector. The component of position vector 3, 2, 4, 3, 2, 4, and the component of the force I, which is 1. For example, let it be this minus of 3 and plus 6. Then torque tau equals 6 times 2, which is 12, minus 3 times 4, minus of 12, I plus j, or minus plus minus plus minus, and the component of j, 2 and minus 3 omitted. Then 6 times 3, 6 times 3, which is 18, minus 1 times 4, 4, j, plus the component of k again here omitted, minus 3 times 3, minus 9, minus 1 times 2, 2, direction k. Then minus it becomes plus, 12 plus 12, 24, I, 18 minus 4, 14, times minus 14, j, minus 9, minus 2, minus 11, k. The unit of torque is Newton meter. Therefore, torque is equal to 24I minus 4j minus 11k. The direction of torque is perpendicular to both force and position vector. Here, equilibrium of a rigid body. Consider a figure below here, and there is a pivot or a fulcrum. Here is a pivot, and there are two forces, F1 and F2. About this pivot, F2 has a rotational or turning effect, which is clockwise, and F1 anti-clockwise torque. It will have anti-clockwise torque. Then from this clockwise torque is due to F1, and anti-clockwise torque, anti-clockwise torque is due to F2 about a pivot of F2 clockwise and F1 which is anti-clockwise or counter-clockwise. The direction of clockwise direction is to the right and anti-clockwise direction is to the left. Here convention clockwise torque is negative convention and anti-clockwise torque is taken as positive. This is the convention related with equilibrium of a rigid body. And now going to second condition of equilibrium.